Okay, welcome back. Check mics. I think so. That's what I'm trying to. Yeah, I'm recording. Okay. Yeah. So the idea for today is mostly discuss what we call the box topology last time. So let's start with that. So today is mostly about the box and the product topology. So already from the title, this is based on 15 and 19 from Bankers. Let me be sure. Yeah, 15, 19. 15 is for finite products, 19 is for arbitrary products. So the main idea here, from the title, with the box product is a product on the Cartesian product. It's a topology, sorry, on the Cartesian product. And if there is another topology called the product topology, that's a more natural name. So that's already telling you the box is not going to be ideal. It's going to have some flaws. And I'm going to convince you today, but also next time, what the flaws are. So what we did last time is you start with a collection of sets. So if you have a collection of sets, you can always compute or define their arbitrary product. That's what we denoted by this big pi over an arbitrary index set of set xi's. And the thing here is, instead of tuples, elements are functions. And the tuple is just a function, nothing too crazy. Then what we did is, if each of these sets xi comes with a topology, xti, sorry, then we defined this thing that I denoted B prime, which is subsets inside of the product where each UI is open in xi. This collection of subsets, they form a basis for some topology. And that topology we called the box topology. That's just the definition. So the box topology we defined, where I'm defining now. We proved this is a basis. And it's a basis for kind of the easy reasons. When you compute the intersection of two of these sets, it's another set of that on that collection. So that B3 that usually you need to find, you can just take the same intersection. Okay, so yeah, I should say this is, I'm defining it now. Defining it now. The proof of why this is a basis? So usually you need to show, we had that famous proposition 3.4. You need to show the entire space, the product space, is going to be a union of things in B prime. That's for free because the entire space is an element in B prime. And then you need to show whenever you have two sets in B prime and you intersect them, so then you need to show this kind of local thing. If you take two sets in B prime and you intersect and you take anything in the intersection, you should be able to find some extra element in the basis. So this is what I denoted by B1, B2, and then you have an X, and then you need to find some B3, should probably be called BX. And in this case, something I mentioned last time, when you compute the intersection of two basis elements, basic sets, the intersection in this case is also basic. So you don't need to like hook up a B3 for each X, you can just take the intersection and you're done. Okay, so that's what we did last time. Now let's start with an example. So example here, very kind of easy. If you have a collection xi, ti, let's say here we have an index z, and assume each xi is discrete. So what I mean by this is the topology is the discrete one, the power set. Everything is open. Yeah.
Oh, wait, just put my question back to when we were proving the topology of the basis. So when you find an intersection, you will find that the intersection of V1 and V2 is a subset of V3, right? Or is it the other way around?
No, the other way around.
V3 is a subset.
But in this case, it's independent because V3 is just the intersection. Yeah. Okay, so if you have a collection of discrete spaces, then the product set here with the box topology is also discrete. So what I mean by this is the box topology on that set is the discrete topology. So how do we prove that the box topology is the discrete one? We need to prove, so to show this, it's enough to prove that singletons are open. Right? That's what it means for any set, for every set to be open. It's enough to show singletons, just one element sets, are open. So let's take a singleton. Let's take an element in the product. Remember, this is just a function. So I'll write what this means. This means A is a function from the index set to the union of the xi's, but with the property that the eighth coordinate is always an element in xi. That's how we define the product. A is a function with that property. This is an I. We need to show the singleton here. That singleton, one element set, is an element of the box topology, but we can just write that singleton as a product of open sets of these four. Take the ith coordinate here. So this guy, this singleton, this set is open in xi because everything in xi is open because it's discrete. So this guy is an element of on the box basis. So of course it's an element of the box topology. So then the singleton is open in the box topology. It's actually an element of the box basis.
Did we want to show that, or we just showed that?
This equality of sets.
Yeah. You said we want to show, and then you wrote this, so I'm wondering.
Yeah, but this equality of sets is trivial. What I want to show is that the singleton is open. What I'm doing here is like showing how you can compute or write down that singleton set using this terminology. And so this set only has one element, the element A. So if you are here, of course you are here. And if you're here, you're here. So it's a set equality, but very easy to prove. It's just a singleton.
This example,
Mhm.
I don't remember the full definition of discrete topology. You don't have to fully define it, but it's
everything is open. This Ti is the power set on Xi. Yeah, it's the finest one. Are we okay?
Well, quick question
Mhm.
on the
the function A as lambda points to, is that a union, right?
Yeah.
The union of xi because of.
Yep. So here to be either so what lives here is something that needs to contain all xi's because I just want the ith coordinate to be an element of xi. But other than that, you could put here anything that contains all xi's. It's not important what this codomain is. The important is that domain and this property. So maybe you can just think of this function in those terms. It's a function with this domain and this property. And the codomain, it's whatever it needs to be. I don't really care about that because I'm imposing some restriction on each value.
That's simply to say A is surjective.
No. No, very far from it. Yeah. So if you're in doubt here, the recommendation would always be go to the finite case. So whenever you're like in doubt here, go to the finite case. Finite case is lambda equals 1 through n. So what I'm saying here is your function is a tuple. So it's going to be a function going out from lambda to something. And something here is going to be the union of xi's, xi, 1, 2, n. Again, this is not very important, just something big. Right? And what I'm saying here is ai is what you usually denote by a sub I. And you want that to be in the corresponding xi. That's what I'm saying. So notice this A is far from being surjective. Unless X, the family of sets xi's is very trivial, pretty much never surjective. Okay, are we good? So that's just one example. So what's going on here? What's going on is I defined the topology on the product set. Now it's hard for me to convince you that that topology makes sense. It's a topology, so it's there. We need to say something about it. But why is it better than any other topology? You could also take the discrete one. You could take like I don't know, the trivial one. Why do we want to take this one? Well, it's there, but is it good? Not really. So here we go. So the kind of the idea. So this is informal. Open sets in box topology. You could either say there are too many, or they can be too small, which is kind of the same because you get to intersect them. But open sets in box topology could be too small. But the thing is, it's very hard for me to justify that argument. I will try to do that either later today or next time. So kind of an example. So here my lambda is going to be positive integers. And my topological space xi is always going to be the real numbers with the standard topology. So here, for all i's. And now I want to consider the box topology. By the way, let me write this. Consider the box topology on the product over I and n of xi. So this is the product over I and n of always the reals. So if your index set is a finite set, you denote this by r to the n, where n is the number of elements. But now this should be called reals to the naturals. It's the only thing it could be. How many copies of the reals we have? One for each positive integer. So this is notation. This is just notation. What I mean by this is just take the same thing, one for each positive integer. So for each of these guys, inside the ith coordinate in xi, we have the open set, this open interval, -1 over I, +1 over I. That's an open interval, so of course it's open. So let's maybe denote this by ui. So do you see where I'm going? These ui's, we have infinitely many of those. Now, so this means this guy here, the arbitrary product over I and n of these guys, this is open in the box topology. So it's an open set containing the function that's always 0. But it's kind of hard to find anything there. It's not empty, but the coordinates of something living in that set, in that open neighborhood of 0, it's going to have entries that need to decrease arbitrarily. So this is too small, and I will justify this later. But this is too small. Too small. If you don't agree, that makes perfect sense. Okay, so let's keep this in mind. Yeah.
So when we are talking about openness of sets in this case, we define it on the standard topology. So it's too small. When you're saying it's too small, you mean when we did the epsilon argument, you could make something much bigger, right? Like you could make an interval much bigger that is contained in the box topology, right? And then doing your like plus or minus epsilon. What do you mean by it's too small?
Yeah, that's what I cannot say now. That's what I just said. Yeah, I need more content to explain what's going on, and that's exactly where I'm going now. So part of what we're missing is this big space contains a lot of coordinates of the real numbers, but we don't know how to relate different topological spaces. We don't know. So we want to use what we know for the reals, like epsilon and so on, but we don't know how, because we just don't know that. And when you want to study things like this, you really, if you study topological spaces, namely sets with something, you need to study functions preserving the something. So yeah, that's where we're heading. So I need to introduce a different definition. I want to introduce a topology that will avoid things like this. Definition 2 for today. Well, yeah. Take a collection of sets. So we don't have topologies here. Given a collection of sets, let's call this xi's, where I lives in the index set lambda. We always have for each index j in lambda, we define the jth projection So this shouldn't be new. You know, from R times R, you have two projections to each of the coordinates. We have the same here as the function. I would like to use pi, but I'm using pi for this and I'm not too good. So I will use p, pj from the product of all these sets to your favorite xj. So notice this things are the same, and this is an arbitrary index, I. So what we're going to do here, given by the pth coordinate of a function A, is going to be the value of A at the entry j, which we know is an element in xj. So this is for any A in the power set, in the product set. So maybe I could say something here. For example, if lambda is finite, 1 through n, then when you do the j of a function with which we can write all the values for, because it's finite, so you can write tuple. Jth coordinate is just whatever aj is. That's the kind of thing we're generalizing. Are we okay? So I want you to note something. What's kind of going on here, the elements in this B prime in the box basis, I want to describe them differently using this piece. I want to have an alternative description. So if you take any subset uj in xj, then its preimage under the jth coordinate, its preimage this guy is going to contain all functions, all tuples, but I want the jth coordinate here not only to be an element of xj, I want it to live in uj. So here I should say pj of a is an element in uj, but this is exactly a of j. So just can write that. There you go. Do you see where I'm going? So let's take one of these sets here. Let's take one of these sets here. Product over j in lambda of uj. This is things in the product. It should use I. This is things in the product where A of I is in ui, or all i's, or all I. So here, this is for this fixed j. But now if I impose this for every j, I have exactly that set. If I impose this for every j, so if I do, instead of every j, I can use I. This is just going to be the intersection over I of preimage under the projection of the corresponding ui. So this is very formal. An element here is a function such that the ith coordinate is not only an element in x, I, but further in ui, in this subset. And here, I'm just saying that for each different I. Are we okay with that?
you trying to make an argument that the space is larger?
Yeah, no, I cannot convince you of that yet. I will tell you when I can convince you. We don't have the tools at the moment. I will at some point we'll have them, but not at this moment. But somehow what's starting to happen here is if you allow arbitrary products of subsets, then in some sense you are also allowing arbitrary intersections of subsets. And you don't really know why, but these sets should be open. If UI is open, this should be open. So we're kind of forcing arbitrary intersections of opens to be open. And that's not very good for any topology. That's usually just too restrictive. But that's what's going on here. So this is an arbitrary open set if UI is open. And this is an arbitrary intersection. I mean, if this guy is open, then this will need to be open. But yeah, these are coordinates. So just generalizing usual coordinates. Yeah.
The inverse notation, because if P is a function of A, right, where but if P sub J A equals AJ, you're feeding in indexing numbers and you're getting out like A's, right? Or AI, A1, A2, A3. So if you're doing the inverse, wouldn't you get out elements?
No, it's not the inverse function. It's the pre-image.
The pre-
Yeah. Yeah, this is the pre-image. Where this is pre-image. So I'm evaluating that on a set. That's already telling you it should be like pre-image.
If you're taking the pre-image of the set, you're just getting that set back. Right? You're getting elements in U and J, right?
No. No, you have a function like this. So pre-image of something here will be a subset here. So it's a subset of the product. So this is like homework 0. I'm assuming you're sharp with pre-images. So what I'm trying to do there is telling you there might be two small open sets here. That's not a claim, but it will be at some point. Sure. Okay, so now with this in mind, let's define something else. So this is going to be definition / lemma, because I want to define something and claim it's something. So the lemma here is, let's take a collection of topological spaces, xi, ti, where I is an arbitrary element in an index set. So a collection of topological spaces. Then the family here, so this is the lemma part. The family I will use S. And here I'm going to write pre-image under P of uj. This is a subset of the arbitrary product. And here I want to let J be any element in lambda and uj be any open set in xj. Then this family is a sub-basis. For some topology. On the on the Cartesian product. And this basis, or this topology, is called the product topology. So that's the definition part. So here for my proof, we only need to prove that this is a sub-basis, right? So only need to show, remember the condition for something to be a sub-basis is very weak. Only need to show that the entire space can be covered using elements in S. So it's the union of elements in S. Right? But in this case, it's even easier if you just fix your favorite J and take uj to be the entire X, then the preimage is the entire set. So this guy is the entire set here is an element in the sub-basis. So we don't even need to check this. So just take your favorite X, your favorite J, your favorite index, and the open xj in the topology tj. So remember, T is a topology on X, so that's always open. But when you compute the preimage under the projection of xj, what you get is the entire set. Because everything here, when you project, you get something in xj. So this is just saying, whenever you have a function from A to B, if you do preimage of the codomain, there is no restriction. It's the entire set. That's what I'm saying. Here, F is just Bj. So that's all the proof we need to write. Are we okay? Now I want to note something about this sub-basis. Remember, sub-basis give us basis, and then that gives us a topology. So if we recall that, when you do Pj inverse of Uj, what we have is we have this. So let me write that. These are functions or tuples. Once again, you're very safe if you want to think about these guys as tuples, but indexed over lambda. So you need to take functions for which the ith coordinate is an element in U. Sorry, ij is an element in Uj. So another way of writing this is I only have a restriction on the jth coordinate. So I could say this guy is just Uj times all the other x's. And I'm doing weird things with the order here. But we allow that when we have infinite sets. Yeah. So that's just an index different from J. So this is mostly formal. It's like what I'm saying here, it's the product of all sets, but for the jth coordinate, I want to restrict to that U. Now, with this in mind, the basis associated to this sub-basis to these subbases is going to be, any guesses? What will happen when I do finite intersection of these guys? So remember, that's what we denoted by B sub S. So this is by definition finite intersections of sets in S. So finite intersections of sets in S. Let's write that more clearly. These are things in S by definition. So it's going to be finite intersections. Let me use a set J, because otherwise I'll need to select finitely many indices in lambda. So finite intersections of things in S. So here I need to say J inside of lambda is finite, and Uj is open in Xj. So what I'm doing is kind of this, but I only allowing finitely many UIs to be different from Xi, because J is finite. So if you like this sort of notation, you can just say this is product over the finite set J. Maybe I need to keep my set. These are sets. So this is product over finite set J of some opens. And then for all other coordinates, I will have the entire X. And here, J is finite. And each Uj is opening Xj. Notice the difference between this and this, the elements in the box spaces. Here you allow each UI to be any open it wants to be, but here you only take finite sets of indices. There you allow any open, but for all other indices, you want the entire space. So maybe I can say, to compare with that, it's going to be products over all i's of UIs. But here, let's say in the box basis, such that UI is different from Xi only for finitely many i's. So it's far more restrictive than this one. I will not allow you to do just arbitrary products as opens as here, only finitely many. And then all other coordinates need to be the entire space. Any questions?
Related to that lemma there, right?
Well, no, at this point, I'm just computing. But to say that this is a basis, I really need to know that S is a subbasis. That's the only way this is related. But yeah, the thing is, I know it's going to give me a topology, in particular because it's going to give me a basis. So here I'm describing the basis. And now the opens are going to be unions of these guys. But the thing is, I'm not letting them be that small, like here. This thing you cannot allow. This is not going to be open in the product topology, because you can have sets that are not the entire space only for finitely many. And here I'm doing that for all of them. So this guy is not open in the product. It's open in the box, not in the product. Yep. Why that's the case? Yeah. So this is open in the box. That's clear. Is that okay? Open in the box because box is just product of opens. Now, not in the product because in the product, you only allow finitely many coordinates to be smaller than the entire xi. You only allow finitely many coordinates to be smaller than xi. That's what I'm saying here. Or maybe look at this one. If you're open, or maybe if you're basic, you're the entire xj in all but finitely many coordinates. This guy is smaller, very smaller than the entire xj in all coordinates. And there are infinitely many of those. Is that okay? So this is way larger than that guy. Maybe I can do something about this. So here, first coordinate is finite. Second coordinate is the entire space. So this is my U1. Of course, with finitely many, I'm going to write that. There's no difference, but just to give you an illustration. This is kind of what's going on here. I need to be sure that some coordinates are the entire space. So this is how an open will look like. That's not true because I need to intersect them and then I will get a square. But here, I'm already doing this kind of thing. So here I'm already doing this times that, and now you have a square. That's kind of what's going on. But the thing is, we can only visualize finite things, and these things are only different when you have infinitely many, when your lambda is infinite. That's why I cannot do an actual drawing. Because this guy is in that basis. Just intersect two of those. Yeah.
Wait, I think I'm starting to understand this. The last lecture, you showed an example of why the box basis is in topology, right? You said if you have two intervals, they can intersect, but then if you have a third one, you have to include all the stuff over here, right?
No, but that was an example of why this is a basis, but not a topology. Yeah, different concept. Yeah.
I think 1j on the board wants to be an I, and it's in the second line from the bottom.
1j on the could be
The xj.
left, 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 left. Oh, thank you. Absolutely. Yeah, there you go. So that's kind of the idea. But again, that's what I'm going to write now. We can only draw pictures with finitely many dimensions, to be honest, at most 3. And these concepts, these two bases, or these two topologies, coincide when your lambda is finite. Why? Because of this. If your lambda is finite, then that's not a restriction. If your lambda is finite, then this last restriction is not a restriction. That's always the case. That set could be empty, absolutely okay. No. But when lambda is finite, product equals box. When lambda is not finite, different things. If you ask me, product is more natural, box is still there. How are we doing with time? Okay. So let's write exactly what I just said, because it's an important thing. Very important, actually. So consequence of what I just wrote, of this last line, consequence, if lambda is finite, then again, this last thing here is an empty restriction. This is always true. Because you could just take all i's. Or maybe look at this thing here. There is no restriction. Do you agree? Yeah.
When you say finite, I assume like the reason that you're negative one over I, one over I, doesn't work is because that is infinite number of coordinates in between those two numbers, right? Like you need discrete, like finite indexes of lambda for it to work, right?
Can you say that again?
Like when you're saying lambda is finite, you can't have an interval, right? Because when you have an interval, you have an infinite number of points,
An interval where?
like negative one over I to one over I.
Like the UI I had before? No, but that was an open set in one of the coordinates. Here, lambda is the indexing set. Yeah, but of course. Yeah, but you shouldn't try to relate this with lambda. You should try to relate the i's here with lambda.
I's have to be finite.
Right, there are finitely many coordinates.
If you have I equals 1, 2, 3, then that would work.
Right. So if lambda is finite, then the bases coincide. Because what I'm describing to be BFS. And then box topology is product topology. And open sets in X1, blah, 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 Xn are unions of what should be called rectangles. UI, blah, 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 UN, where each UI is open in Xi. Sorry? So I'm saying each UI is open in Xi. Okay, so now maybe before we move on, I want to, so this is a fact that you will prove. Remember, to introduce the box topology, we used a basis that we call the basis topology. And what I mean here, if you have for each xi a basis, so for each topological space xi, you have a basis, let's call it bi. Then instead of using the box spaces, we can use something smaller than this thing. How do I want to call it? Maybe let's use no name. Products of, instead of using UIs, I will use PI, where maybe let's say these are subsets of the product of all x's. But now instead of asking for BI to be open, I will just ask for BI to be a basic set. Then this is a basis for the same thing, for the box topology. So that's a homework question for you. And of course, if you only allow finitely many BIs and ask all of the others to be the entire XI, then you'll have a basis for the product topology. So as an example, because it's kind of embarrassing at this point that we don't have a topology on Rn. As an example, consider R to the n, which is just R times R times R n times where we have the standard topology with the box topology, which is the product topology, because we have finitely many. And here I would take standards for each copy. It's standard, standard, standard. So we know for each copy, we have a basis of open intervals. So here we have a basis. So here we have the basis for this topology using the fact is sets of the form A1, B1, first open interval for the first entry, A2, B2, blah, 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 AN, BN. And here I just, let's say AI is smaller than BI for each I. So here opens are going to look like, I don't know, Q or something. Yeah, maybe 3 dimensions, that's too much. And then unions of those. So opens, unions of those. And this is basic. Yep.
The question I should ask one time ago, what does base mean again?
An element in basis.
Is it an element base?
Yeah. So let me just mention, this is the first topology that we have for Rn. It's the product or the box, because it's the same. Opens here are unions of these squares, or well, rectangles, to be honest. If you're familiar with this, you expect open balls instead of squares. And that we will address. We'll come back to this when we study metric spaces, and there we'll discuss open balls. And maybe those guys will be open balls, who knows? We'll come back to this. But at least I'm happy we have one topology on R to the n. So we have 5 minutes. In those 5 minutes, I will start to build the tools that I need to justify that this box contains open sets that are too small. Yep. No, well, I'm kind of keeping the same notation. So XITI should be some open collection of topological spaces. Yeah.
Oh, I see.
Yeah. Yeah. Sorry about that. So I'm assuming I have a collection of topological spaces, and for each of those, I have a basis. In that case, for the box topology, instead of taking arbitrary products of opens, you can take arbitrary products of basic sets. And that's going to give you a basis.
one, B1, they are really.
Yeah, they are real numbers. So those are open intervals. Yeah, each of those is an open interval. Because remember, that's the standard basis for the reals. Okay, very exciting new topic, continuous maps. Of course, we are not going to discuss much today, but I want you to start thinking in these terms. Continuous maps. So this is based on section 18 of the textbook. So this should be definition 4 for today. So today, I went kind of slowly. I recognize that. Sorry if you get bored. The idea was arbitrary products are hard, very hard. And then we have these two topologies which are different only when the set is infinite. So we can't even draw pictures. What I'm doing now is telling you, if you want to understand space, you need to understand functions. Because sometimes that's all you have. So definition 4. Let's take two topological spaces, X and Y. So here I'm not writing the topologies. Two topological spaces. And let's take a function. So we say that a function f from x to y is continuous so I would use function and map with no distinction. So we say that a function is continuous if for each open u in x, the preimage f inverse of u, which is a subset, each open u of y, the preimage, which is a subset of x, is open. Remember, open just means an element in the topology. I completely understand if this sounds arbitrary. Next time, we'll start the class with a proof, with theorem, explaining why this makes sense. So some examples. If you have a topological space, X tau or T, topological space. So notice a function is going to be continuous or not, depending on what topology we impose on the set. It's not just about the function, it also depends on the topology. Then the identity map from X to X, which takes, remember, identity, maybe let's use I sub X of A equals A, is continuous. And that's because if you do identity of X preimage of U, you just get U. So if U is open, it's preimage, it's also U, it's open. More generally, but not really, if you have two topologies on X, X T1, or maybe let's say, let's have two topologies on X. Let T1, T2 topologies on X. And I will leave the class with a question. Then the identity map of X going from X comma T1 to X comma T2. So what I mean by this, it's a function going out of X to X, but I want you to consider two different topologies, T1 on the domain, T2 on the codomain. This map is continuous if and only if T1 is blah than T2. And blah should be finer or coarser. And that being said, let's stop here. Pause the recording.